detailed set problems. I think I stopped somewhere with number 7. Detailed set 7 has 2 times n minus 1 disconnected Pareto optimal regions. And all these problems, something I forgot to mention yesterday, is to use these test problems, you have to define a certain number of decision variables. And there are rules for that. It's not an arbitrary number. Normally, these test problems, the detailed set, are used with at least 3 objectives. It's possible to use them with 2, but it's rather uncommon. So in this case, this problem is meant to test the ability of a multi-objective evolutionary algorithm to maintain simultaneously regions at different solutions at different regions of the space. And this is the last picture I showed you yesterday. So you can see the 4 portions. This is actually a very difficult test problem. Detailed set 8. It's in this case, the number of decision variables must be larger than the number of objectives. And the problem also has constraints. And the Pareto Front is a combination of a straight line and a hyperplane. It's actually also a very difficult problem. The difference is that this one has constraints. Detailed set 9. So normally the decision variables is 10 times the number of objectives. And the true Pareto Front is a curve, similar to DTL set 5, but the density of solutions decreases as we approach the Pareto optimal region. So here the Pareto Front is at the intersection of all the constraints, which is meant to be the difficult part. So it looks very complicated to reach. Okay, so we mentioned yesterday the set DT. Those are very old test problems from 2000. DTL set, they were proposed in 2004, in 2002. They are still used, but there are other benchmarks. Before we get to WFG, which is considered one of the most difficult benchmarks today, there is this very interesting paper, was published in 2004. It was part of the PhD thesis of this guy, Tatsuya Okabe, who got his PhD in Germany. And basically, he proposes in the paper and also in his thesis a methodology to generate multi-objective test problems based on a mapping of probability density functions from decision variable space to objective function space. And he provides in the paper 2 examples, but in the thesis you can find more. So the idea is we depart from an initial space, which is called S squared, between decision variable space and objective function space, and from there we have to build both the spaces applying a certain function. In this case, they propose to use the inverse of the generation operation. So it's deformation, rotation, and translation. Well, the 2 problems I'm going to show you, this is Okabe 1. If you can see, it only has 2 decision variables, but this problem is actually very difficult to solve, although it only has 2 decision variables. So the Pareto optimal set is located here. Here is the Pareto Front, so you can get the exact expression. And they use this parameter, the distribution indicator, that measures the amount of distortion that the probability density suffers in decision variable space under the mapping from decision to objective function space. So this is decision variable space. No, this is objective function space, is the true Pareto Front. And this is decision variable space. So something really interesting about this problem is that the mapping between decision variable space, this one, and this, is highly nonlinear to such an extreme that sometimes you have a solution that is very close here. It looks like you almost reach this curve. You are slightly above this. But when you plot it in objective function space, it's really far from the 2 Pareto Front. So even a small difference in decision variable space is a huge difference in here. So the Pareto Front will be over here. So it's very challenging. It's so difficult that for many years, most people didn't include these test problems. Even today, they are not very common. This is the second one. Again, only 2 decision variables. This is the Pareto optimal set, the true Pareto front, and the parameter, the distribution indicator. So you can see again, this is the true Pareto front, and it looks really strange. This is the decision variable space. This is the Pareto set. So again, you could be able to generate an approximation that is very close here, but if you don't match this exactly, then the Pareto front is going to be somewhere, not here, but below. And there will be a big gap. So these are very interesting problems, very challenging. That's why most people don't use them. In 2005, first, these guys from Australia, Simon Huban and several other people, they proposed a toolkit to design test problems. Then the extended version of this paper was published in the Transactions in the year 2006. This methodology, this toolkit, is known as the Walking Fish Group. It's a very strange name, but that's the name of the group in Australia. And these are very difficult, very challenging test problems. Today, most people use them, but they started to become popular probably after the year 2013. Before that, most people didn't use them because they were just too difficult to solve. So I won't get into the details. They have a whole sort of transformations. These are the shapes of Pareto fronts. Many, you can see deceptive, multifrontal, non-separable, flat, all kinds, concave. And based on those transformations, they define the test problems. So this is, for example, the first, WFG1. In all cases, this is the decision variables vector. And this is, for example, the true Pareto front of WFG1. In the year 2006, I had a student who was working on designing a variation of the epsilon constraint method using differential evolution and something we call a cultural algorithm. And he came out with a very interesting algorithm that was very powerful. It could solve really difficult problems, but it required a very high number of objective function evaluations. So we had the dilemma that we didn't know how to justify such an algorithm. It's possible to justify a very costly algorithm only if it can solve problems that nobody else can solve. So at that time, the WFG problems were very useful for that because, for example, the second one, the WFG2, at that time, 2006, we tried algorithms like NSGA2, and not only NSGA2 was not able to converge to the true Pareto optimal front, but at some point of the search, NSGA2 will start moving in the opposite direction of the Pareto front. Most algorithms at that time exhibited a very strange behavior with these test problems. The reason has to do with some of the transformations they use, because they have, for example, in some cases, these exponentials that with a small movement, you can make a big jump, similar to Okabe's test problems. So if something goes wrong at some point in the search and you generate a solution that deviates the search a little bit from the original direction, then the objective function value will tend to favor the movement in that direction, and you will be drifting away from the Pareto front. So it's very, very interesting. These problems are still very challenging. Now, something that some people have criticized about the WFG test problems is that they propose a methodology. So we were supposed to use the methodology to build new test problems. But nobody did that. Everybody took the test problems that are shown in the paper. But the idea was to design others. Nobody has really done that. It's of course possible, but nobody does. So WFG3, this is also very, very difficult problem. It looks like you only have to generate a straight line, but it's very difficult to produce it. WFG4, this is like a fragment of a cone. 5, it looks similar to 4. 6, looks also very similar. You will see in some cases the quality, it looks like it has holes. This has to do with the resolution we use to generate the true Pareto optimal front. But all these problems have a closed form. That means we can plot it. We don't have to generate it by brute force. This is WFG7, 8, 9. 9 looks really nasty. Now, these test problems, one of the rules, because what happened is, at some point, when people started to use them, and many researchers realized that they had to incorporate these test problems because otherwise their papers would not be accepted in a specialized journal, they realized that it was easier to solve these test problems if you reduce the number of decision variables. However, in the paper, they are very clear that at least these test problems, they have to be solved using at least 24 decision variables. I have seen people who have used 12, 14, 20 decision variables. If you decrease the number of decision variables, the problem becomes easier. You are supposed to use at least 24. Otherwise, you are cheating. Right? You are solving an easier instance of the problem. With 24 is quite difficult. It's possible, but difficult. Okay. Other test problems, people over the years have proposed other methodologies, but none of these other methodologies are used extensively. Like, perhaps a few people have used them, but not that many. Some of them are quite interesting. For example, this one, the Lamé superspheres, proposed by Michael Emmerich and André Dutz in 2007. This is a scalable test suite that is based on this concept of the Lamé superspheres. It has the limitation that the Pareto optimal geometries considered have spherical shapes. But it can be considered as the first study that is focused on the Pareto shape of the multi-objective test problems. Something really interesting about this test suite is the mirror test problems that they propose, because these adopt an inverted sphere as the Pareto shape. So it's something very interesting. Huban already mentions these mirror functions, but you will see why they are important. Towards the end, I will show you why these mirror problems are important. This is Michael Emmerich. So in addition to new Pareto optimal shapes, these Lamé superspheres incorporates features such as multimodality and many-to-one mapping. And these are sort of additional difficulties, sources of difficulties for testing a multi-objective evolutionary algorithm. It's built upon the DTL set framework, so it also has distance and position parameters, same as the DTL set. Other people have analyzed other difficult or complicated Pareto sets. For example, Saxena, he extended the principle of complicated Pareto sets that was introduced by Xin-Fu Zhang. This is a well-known paper. This was derived from a competition. In 2009, there was a competition at CEC, the Congress on Evolution and Computation. The winner was Moiadi. These test problems are known normally as the UF test problems. It's not very common to use them, but some people have used them. They are called the UF. And in this paper, they analyze some of these problems. Something interesting is that The version that won the competition in 2009 is available in the public domain. You can download the code. But if you use that version of MoIAD with the DTL set problems, it has a very poor performance. And if you take regular MoIAD, it does very well in DTL set, doesn't do that well in the UF. So that means they are sort of tuned, right? They modify something to the algorithm. It's not the same algorithm. It has some differences. So, well, Saxena in 2011 proposed another test suite, this Saxena San Duro Tiari. Is this one, was presented at IMO in 2011 in Brazil. It introduces 7 unconstrained test problems, and there is a methodology to design new test problems. This one is very rarely used. Very few people use this one. In these problems, the Pareto optimal fronts are defined in 1 and 2 dimensions, so they generate for more than 2 and 3 objectives. And regarding Pareto optimal fronts, 4 continuous and connected surfaces, including convexity and concavity, generalize the Pareto shapes in this case. So the convergence difficulties, why is that these problems are difficult? They rely specifically on the topology of the Pareto sets. Remember, Pareto set, we are talking of decision variable space. Pareto front, we are talking of objective function space. The main disadvantages of this test suite is the absence of multimodality and non-separability. But it's kind of an interesting proposal. They use a modular approach, which makes it difficult to determine position and distance parameters, and this is something good because it makes the problems more challenging. Another ingredient that is very interesting to introduce is large scale. For many years, we didn't have a benchmark that considered large scale problems for multi-objective optimization, only large scale for single objective. That we had competitions for many years. Why is this important? Because today people are already designing test problems for large scale. What do we mean by large scale? Any multi-objective problem with 100 decision variables or more is considered large scale. Less than 100 is big, but not big enough. It's not large scale. How far can we get? Well, some people have designed multi-objective evolutionary algorithms to solve problems with up to 5,000 decision variables. That's how far we have gotten so far, but the aim is to reach perhaps 10,000. Yesterday, I mentioned a problem we had to solve some years ago that has 13,000 decision variables. There are, of course, problems with 1 million decision variables. Those problems exist, but in general, it's very difficult to use anything to solve them. So before this benchmark was published, you see it's very recent, from December 2017, just 3 months ago. Before this benchmark existed, people use the ZDT or the WFG. Those are scalable in the number of decision variables. You don't have to increase the objectives, you can just increase the number of decision variables. But it's nice to have a benchmark. Something that Human discussed in his paper is something we call the variable linkages. This concept refers to possible interactions among the decision variables. There are some problems in which the modification of one decision variable affects others in the same string. Some people have analyzed those problems for multi-objective optimization. It's not very common, but when we have this situation, this dependency, the problem becomes very difficult to solve. So for example, I have here a problem with 20 decision variables, and it may happen that modifying x2 affects also x12. Now, x2 somehow is related to X12. So if I modify something here, this has an effect also in X12. This problem in evolutionary computation is known as epistasis. If a problem has this condition, it's very difficult to solve by an evolutionary algorithm. If it has a very high epistasis, no evolutionary algorithm can solve it. There are some special algorithms for that, but in general, those conditions are very rare, but some problems have it. It's possible, of course, to introduce artificially the condition. Some people have done that as well, and that is what is known as variable linkage. There is some sort of relationship among some of the decision variables in the problem. Okay. In these large-scale multi-objective problems on this new benchmark, the variable dependencies are stated by two linear variable linkage functions that are linear and nonlinear. So besides having many decision variables, they introduce this dependency of the variables. So there is also a correlation between decision variables and objectives through a correlation matrix. And although in the benchmark, the test problems are scalable to an arbitrary number of objectives, they only basically use it with up to 3 objectives, which is something interesting because, as I mentioned before, if you have more than 3 objectives, that problem is called many objective. Is k greater than 3, the number of objectives. If the number of decision variables is more than 100, it's large scale. What nobody has solved so far is a large scale many objective problem. Something that has many variables and many objectives. At least so far I haven't seen anybody doing that. It will be very challenging to do that. Okay, another toolkit was proposed by Masuda in 2016. This is also very recent at CEC 2016. This is a toolkit to generate scalable test problems, and it's focused on the design of different Pareto optimal shapes. And in this case, the methodology allows the design of Pareto optimal surfaces using a finite number of vertices. And these vertices state the Pareto optimal front, whose shape can be defined as linear, concave, convex. There are several possibilities. In the paper, they only instantiate 2 test problems, but the paper contains, again, a methodology so that people can develop more. This is quite interesting, actually, from Hisao Ichibuchi. Something remarkable of this test suite is that at different distances from the Pareto front, different Pareto front shapes can be produced. And this makes the problems much more challenging. It's actually a very interesting feature that is uncommon in all the other benchmarks we have. Then we have the multi-line distance minimization problems. This is even more recent, was published last month in the Transactions. In this paper, they propose a class of scalable multi-objective test instances called the multi-line distance minimization problems. And the idea is to assess performance of evolutionary approaches in high-dimensional objective space. So it's for many objective optimization, we will say, which is the reason why it's called like that. And the test problems that are proposed here were introduced for visual examination of solution diversity in decision space rather than in objective space. That girl is Crina Grosan. She is from Romania. So this test suite has 2 main characteristics. First, the Pareto optimal solutions lie in a regular polygon in a 2-dimensional decision space. And second, these solutions are similar in the sense of Euclidean geometry to their images in high-dimensional space. So this allows us to understand the distribution of the decision variables, so decision variable space, by observing the solution set in this two-dimensional decision space. So it's, as I mentioned before, is meant to help us visualize solution diversity for problems that have many objectives. So it's quite interesting. More recently, and this is also very, very recent result from Ichibuchi, he presented this first in 2015, but 2017 has a full paper on this. He proposed what he called the minus versions of the DTL set and the WFG test problems. This is nothing but the inverted test problem, 1 divided by the original test problem. So these problems have many of the original properties of these benchmarks, but the reason why he proposed this is because he realized that decomposition methods such as MOIA-D are not able to solve the minus versions of the problems. They can solve the original version, DTL set, WFG, but if you get the minus version, the technique they use to generate the weights doesn't work properly. And then the algorithm produces an approximation, but it's very bad. So this is a very interesting finding because right now many people are working on this, on trying to design algorithms that can overcome this disadvantage of decomposition methods. So far, nobody had found any disadvantage of decomposition methods. This is the first serious disadvantage. So it's very, very interesting. What they discuss in the paper is that if we use the inverted versions of the Pareto fronts of the DTL set and WFG test problems, we obtain a similar effect as in the mirror Lamé superspheres test problems from Michael Emmerich. So that's also a very interesting result. So in this test suite, different geometries are adopted instead of just being limited to superspheres, as in the case of Michael Emmerich's proposal. And some important points to consider are, first, that all the test problems maintain the same properties. This is what I already mentioned, respect to the difficulties of the distant functions. And second, different test problems promote the design of diversity mechanisms to achieve a proper representation of the inverted Pareto optimal fronts. So this second issue means that diversity becomes very important. The density estimator is very important in these problems because if you use the conventional methodologies, for example, the methods to generate weights in decomposition methods, then you cannot solve the problems. I believe algorithms like NSGA3 also have difficulties with the minus versions of these problems. So this is now a very hot topic because we found something that the powerful algorithms we have today cannot deal with. So people are already working on how to fix this. Okay, another one is this MAF, Cheng, also very recently, last year. He presented a compilation of 15 test problems, which are presented as a scalable test suite. It's called MAF. And in this test suite, the idea is to compile a set of test problems with different features to evaluate many objective evolutionary approaches. Most of the problems in this test suite were taken from the WFG, DTL set, and another test suite. So it's not really anything new. It's just he tries to compile what he considers is relevant for many objective optimization, problems that are scalable. Okay. Summarizing, in general, there are 3 different techniques that have been adopted for constructing multi-objective test problems. We have the so-called multiple single objective approach, the bottom-up approach, and the constraint surface approach. So I will explain very briefly the difference between these 3 approaches. So first, the multiple single objective. This is a very simple, I will say, intuitive method in which we combine several single objective optimization problems to formulate a multi-objective model. If you remember from yesterday, we described this methodology from Kalya Muidev, 99. He did something like this. He posed two single objective problems, put them together, and this created a problem with two objectives. So in the early days, several people adopted this. But the main disadvantage of this approach is that the Pareto set and the Pareto Front are unknown. And depending on the single objective functions you use, they could be very difficult to obtain. So they don't have a closed form. That means you will have to enumerate all possible solutions to generate the true Pareto optimal front. So it becomes difficult to analyze results, to compare results. But recently, some people are using again this methodology. It has some advantages because the single objective can be a very, very difficult problem. So today, for example, there are some people in some research groups that are trying to extend a methodology that was originally proposed for single objective. They are trying to extend this to multi-objective. And this is called the black box optimization. Dimo Brokov and a few other people who are in France, they are working on this, and they have a whole library that they developed with some very difficult single objective optimization problems, and what they are trying to do is to generate, based on this single objective, generate problems with two objectives that are difficult. However, even if the single objective problems are very difficult, once you put them together, that problem with two objectives is not necessarily difficult. That's the funny thing about multi-objective. It could be difficult, but we don't know. It depends on the trade-offs. It doesn't depend on the complexity of the single objective. So even if you put them together, there is no guarantee this problem is going to be difficult. So second approach, the bottom-up approach. This is what was used, for example, for the DTL set. In this case, this is more flexible, and the idea is that the Pareto optimal front, the objective space, and decision space are constructed separately. So we have the so-called position and distance parameters. So the decision variables are clearly divided. And the Pareto optimal surface, the Pareto front, is constructed using parametric functions. These are called position functions that take as an input the position parameters. So this is very nice because you can have what we call a closed form. So you have an equation that generates the Pareto optimal front. So you don't have to generate this by brute force. So you are building the Pareto optimal surface using this equation, and you use also some bounds on objective function space and do the mapping from decision variable space to objective function space. So it's a very nice methodology. Many people like this because it offers many advantages. So in this case, you can define linear or nonlinear functions in which the inputs are the distance parameters, and these functions that we call distance functions establish the distance of the objective vectors to the Pareto front. So in this case, the difficulty of to approximate solutions to the Pareto front depends directly on the difficulty of solving these distance functions. So in here is where you have all the source of difficulty of the problems. So this has been used a lot, particularly if you want to design scalable test problems. However, the weakness or the disadvantage of this approach is that normally position and distance parameters are assumed to be completely uncorrelated. And this is something that has been criticized because this will be rarely the case in a real-world problem. Normally, in real-world problems, the two types of parameters, position and distance, will be correlated to some extent. So that's really the limitation of this approach, but it's very nice. It makes things a lot easier for the user. For the designers, perhaps not that easy, but for the user, it's very easy. So the last approach, the constraint surface. In this case, this approach was introduced to construct constrained multi-objective test problems. Kaljamoidev used this. And unlike the bottom-up approach that starts on a predefined surface, in this case, the constraint surface states the overall search space. That's the starting point. Then a number of linear, nonlinear constraints that involve the objective functions are added, and these constraints, of course, remove or delete a portion of objective space, and other linear, nonlinear objective functions are defined, and you do the mapping. So it's a kind of, we can see it as a variation of the bottom-up approach, because in here, of course, what you are trying to do is to introduce the constraints in such a way that you can still have the original Pareto surface that you generated for the unconstrained case, and the constraints are located in such a way that they don't modify the main features of the problem, the ones that the problem had without constraints. So it's tricky to do it, but it's possible. It's not that difficult. The criticism is the constraints are not going to be that difficult to satisfy. So that this can happen, the constraints are normally easy. You cannot make something really elaborate. Some recommendations, well, the construction of multi-objective test problems should satisfy certain requirements related to some features, some characteristics we would like to see in those test suites. And what we really want to do is that a test problem evaluates somehow the robustness of a multi-objective evolutionary algorithm. That means the capability of the algorithm to solve a test problem that has a certain number of features, not only one. If you design an algorithm that is very good, for example, for disconnected Pareto fronts, okay, that's good. But if it cannot solve a problem in which the Pareto front is connected, then this algorithm is of no use, because connection is considered to be an easier condition than disconnection. So you will expect an algorithm that can handle disconnected should also be able to handle connected. So normally the easier condition is pre-assumed by the user. You know, this is more powerful than something that can only solve connected. But that doesn't always happen. Sometimes there are some algorithms that are very strange and seem to be good only for difficult problems and not for easy problems. So there are several criteria that have been discussed by several authors regarding the construction of multi-objective test instances. This is Huban. So for example, Huban, he analyzed, it's Windows again. He does it every day, right? There we go. So Huban, for example, he analyzed and justified several requirements that should be considered in the design of multi-objective test problems. So we will show that in a table. And he also, the ones that have R are recommendations, and the one with F are features. And we added a few more. Actually, we have a paper, a survey on multi-objective test problems that is almost accepted in the transactions. We hope it gets accepted soon, so it can be published probably next year. So let's take a look at the recommendations. All the ones on top are recommendations, and these are features. So we have, for example, no extremal parameters. This prevents exploitation by truncation-based correction operators. No medial parameters prevents exploitation by intermediate recombination. So in each case, there is a reason for this. So what does this mean? Okay, I should have a problem such that the solution is not in the extremes of the Pareto Front. Because if I put it in the extremes, it may happen that the operators exploit this information. Also, I should not put it in the middle. If you remember the DTL set test problem we saw yesterday, one criticism of the DTL set is that several of those test problems have the Pareto optimal set in 0. So it could happen that because of the nature of the algorithm you are using, at the beginning of the search, you initialize the decision variables in 0. If you do that, you are already in the Pareto optimal form. You already solved the problem without doing anything, just with the initialization. So this is wrong. So the solution should not be in a position that is easily reachable. So this actually happened to us several years ago. I had a collaborator who had designed an algorithm, and it looked so good because it could solve DTL set problems very quickly. But it was not that the algorithm was so good. It was that he was initializing decision variables in 0. So another recommendation is scalable number of parameters, because this increases flexibility and demands scalability. Also a scalable number of objectives. Parameters is, of course, decision variables and these objectives. Dissimilar parameter domains. This is also interesting. This means don't put the same range to every decision variable. Because normally you assume, okay, I have 20 decision variables. They are all between -10 and 10. Try not to do that. Why don't you put some decision variables between -10 and 10, others between -20 and 5, and so on. Because these will encourage the mutation operators to do their work. Otherwise, it's not that challenging, really. The similar trade-off ranges. So you don't want the trade-off to be always in the same range of the decision variables. You want these to move to different ranges. Pareto optima known. This is important because if we don't know where the solution is, we will have to put a lot of effort to figure that out. It takes a lot of computer time. So features. Pareto optimal geometry should be convex, linear, concave, mixed, degenerate, disconnected, or some combination of them. Parameter dependencies. Objectives should be separable or non-separable, so you should have both in the benchmark. Bias. Substantially more solutions exist in some regions of fitness space than they do in others. Many-to-one mappings. Pareto 1-to-1, many-to-one, flat regions, isolated optima. All this is important because each of these conditions is testing the ability of the algorithm to do certain type of exploration. Modality, unimodal or multimodal, and this includes possibly deceptive multimodality. A difficult Pareto set topology, so a Pareto set that is difficult to characterize, rather than using a regular shape like a sphere. Try to use a non-regular shape. Difficult Pareto Front shape, correlation of position and distance functions, and single optimal solution for a high number of objectives. So all these are very important features. Some limitations of the benchmarks we have today. Well, all of them follow the bottom-up approach, the ones that we are using today. And this, as we mentioned before, splits the construction of the Pareto Front and the design of the search space, which facilitates constructing the problems in high-dimensional objective spaces. The first 7 recommendations I put in the table are partially covered by most of these test suites. And the best in terms of these recommendations is the WFG, which is not surprising because it was Huban, the guy who recommended this. In the case of features related to the search space, from the 2nd to the 5th, most of the modern test problems do not adhere or cannot fit in a specific or desirable combination of features. They include some, but not combinations of them. And there is no reason, of course, to assume that a real-world problem is not going to have a combination of features. What I mean by combination is that the same test problem does not include more than one feature from this list. Normally, they include one at a time in each test problem. So one might doubt the existence of multi-objective problems having a combination of characteristics is different from those in the existing test suites, but these problems should exist by the no-free-lunch theorem that I mentioned before, because there is an immense number of formulated and unformulated real-world problems, and it's reasonable to believe that any of them will have a wide variety of features that are not already included in any of the test suites we have today. So if we don't have flexibility for adding these features, this is, of course, a limitation of the test suites we have today. And finally, difficult Pareto set topologies, which is the sixth feature. Don't forget that Pareto set refers to decision variable space, are not considered by most of the modern test suites. And this, of course, becomes another limitation. So something important to consider in scalable test problems is the shape of the Pareto optimal front, because the existing scalable test problems combine different geometries that we already know: convexity, concavity, linearity, and so on. And several of the existing test problems can be characterized by an n-1 simplex. And these test problems having these sort of shapes are easy to solve, in a sense, not so easy, but relatively easy to solve by an evolutionary algorithm. We also can find multi-objective problems in which the Pareto front approximations draw very strange geometries that do not follow exactly the shape of an n-1 simplex. But these problems are normally not included in the benchmarks. Most of the modern test problems do not follow the 7 feature that I put in the table, which has been suggested to evaluate diversity. The 7th feature is the difficult Pareto front shape. So this is a limitation because we don't have it in most of the test problems we have today, and this, of course, motivates the design of new geometries. Because why is this important? Because we saw diversity yesterday. The density estimator is a fundamental component in a multi-objective evolutionary algorithm. And the fact that we can converge is important, but not only we should be able to converge, but also to spread solutions in all the Pareto front. So this feature has to be measured somehow. And we do have a performance indicators, that's the next topic. But we need to have also test problems to validate this. Another property is feature 8, is the correlation between position and distance functions, because most of the modern test problems do not follow this property. There are, of course, approaches that can correlate position and distance functions, but it's necessary to do more research in this area. So this is what I have on test problems. I don't know if you have any questions so far. There are, of course, other test problems that I did not mention here, because I tried to focus on, for example, we do have combinatorial. We have vehicle routing. All these are multi-objective instances: scheduling, layout, knapsacks, spanning trees. All this has been solved using multi-objective evolutionary algorithms. I'm not talking about these problems in particular because we, well, first, I don't work in that area, and second, we don't have enough time to cover that. But those problems, of course, exist, and there are people who have worked on that. So in case you are interested in knowing more about those problems, I think I showed you the email repository. It's right here. allow me to go through.
Yes.
This is tough. Okay, let's see if this works. Yeah, it worked. So, in case you are interested, you can go to the EMO repository. We do have now a search engine. So you just put a term, for example, vehicle routing. You want to know what papers do we have in the repository on multi-objective vehicle routing. So just put it, and you will get the hits. And you will find, in a few cases, not that many, we have the PDF. But in here, for example, vehicle routing, you will see we have 7 pages of results, so it's quite a few. So in most combinatorial problems, we do have a lot. You go to scheduling, you have to be clear what you mean, what sort of scheduling, because otherwise it's 57 pages of references, because we have job shop, we have production scheduling, we have flow shop. I think somebody asked me about grid scheduling. And we do have grid scheduling in the repository. So we have more than 11,000 references in the repository. So just put the topic that you are interested on, and you will find references. Or you can ask me in case you forget the link. But the link is very easy. It just moved. It was somewhere else, but it's. This is the link. And in here you can also find software and other materials that may be useful to you. Also the statistics of the repository, the graphs that I show you with number of papers per year, all this is here. This is updated almost every day. And you can see also by, for example, you want to see PhD thesis only, you will find, depending on the last name, you choose a letter, and you will find the thesis there. There are, for example, for C, you will find my thesis somewhere there, from 96. Yeah, there are quite a few. I must be in the 3rd page. Yeah, that's me, not the guy above. I know that guy. That's Coelho with H. Yeah, so yeah, you can find a lot of information in the repository, and the search engine, I think, is very useful. Okay. So let me see before we move to the next lecture, which is on performance indicators. I think I had, yeah, this is just for those of you who are interested in doing research in evolutionary multi-objective optimization. If you plan to validate a new multi-objective evolutionary algorithm, the most common test suites that have to be adopted, well, SetDT, as I said, not many people are using this one anymore, but you can use it if you want. It's more common to use DTL-set and to use WFG. Those two are the most common. As I mentioned, the problems in this case are meant to be used with at least 24 decision variables. This, of course, is for continuous. If you are doing combinatorial, it's a completely different story. So, and as I said, summarizing, test problems are meant to include features that are relevant to validate multi-objective evolutionary algorithms, for example, concavity, disconnections, multifrontality, deception, and so forth. And as I mentioned before, a common complaint has been that these benchmarks don't include features of real-world problems. For example, uncertainty or a high computational cost of evaluating the objective functions. It's true, these features are not there, but the main reason for that is that it's very difficult. If you ever work with a company, you will see that companies will make you sign a confidentiality agreement. So they will allow you to see all the details of the problem they want you to solve, but that doesn't mean you can make public this information, because this information has some monetary value, right? It's worth a lot of money for the company. And they don't want the competitors to know what sort of mathematical models they are using. So they're not going to be that happy to share this information with the rest of the world. So that's one of the reasons why this is very difficult. There have been stories about people who tailor their algorithms for specific test suites, and therefore these algorithms are very good for the test suites and not that good for real-world problems. That is, of course, true. Many people know, for example, NSGA2 is very good in the DTL set problems, at least most of them. And other algorithms are probably not that good. Today, there are more algorithms that are good, but some years ago, other algorithms were not that good. But NSGA2 was developed before DTL set, and the developers of DTL set included Deb, who developed NSGA2. So he certainly tested his algorithm in this test suite. So yeah, this, of course, is sort of unavoidable. And the other one I wanted to show you before we move to the next topic is a little bit more of detail of algorithms such as NSGA2. Probably you are very familiar with it. This is actually a picture from the paper on how it works. NSGA2, as I mentioned, consists basically on taking a population of a genetic algorithm. It's a genetic algorithm, normal genetic algorithm, applies the non-dominated sorting. These are the layers that it produces, and then it selects based on Pareto optimality and based on the crowding distance value. So this is the non-dominated sort. This is the algorithm, including the paper, which is not that difficult. You remember this preg symbol is meant to say dominates, if P dominates Q. So you can follow the algorithm. It's not very complicated. Crowding distance we already saw. We form a cuboid. This is the solution in which I am, and I check the previous and the next solution to compute this. And this is the crowding distance assignment. This is how it is done, by measuring these distances. So it's very, very easy to do. And in the operator, it guides the selection because we check first non-domination rank, and second, the crowding distance. So the partial order is modified. So I goes before J if its rank, that's non-domination rank, is better, or if they have the same rank and its distance is greater than the distance of the other guy. So if there is a tie, we use crowding distance. So it's very, very simple idea. And you can download the code from, there are perhaps other places. My advice is do it from Kalyan Moidev's webpage. This is his website in the US. He was at Kanpur for 20 years. He's now in Michigan State, in the north of the US. And if you go to that link, I think it will work. You will find several versions of the, oh, it's very small. Yeah. You will find several versions. They are sorted by date. So you can see the original one is this, and then there are revisions up to 2011. The original one is the only one that says for Windows and Linux. So if you are Windows people, you should stick to the old one. All the new versions are only for grown-up people, only for Linux, 64-bit for Linux. He also has his other algorithms, like the epsilon MOIA that we talked about yesterday. The Omni optimizer, we didn't talk about this one. And this is a micro GA he developed with an Indian guy. And this is the original NSGA is now there, finally. So if you wanna get the code, you can go there. And my advice is, if you develop something, you should put it in the internet or don't publish that, because if you want people to use it, you have to put the code. Don't be afraid. MOIA-D. MOIA-D is based on decomposition. As I said before, this is the basic algorithm. So we have a population, and we have these FB values, objective function values. It uses an external archive. This I didn't mention, but it uses an external archive. And then what the algorithm does is it produces n weight vectors, and these vectors define the search directions we are going to use. And he runs his single objective optimizers in each of these directions of the weight vectors, and uses neighborhood exploration, so that one set of individuals that are solving the optimization problem in one direction is helping the others that are close to it. That's why the search is very efficient. This algorithm is actually very, very fast. So this is all the detail of the algorithm. I won't get into all the details, but it computes Euclidean distances between the weight vectors, generates the population, initializes the population, applies reproduction. Then the improvement is basically the operators, apply the variation operators. The neighboring solutions are updated here, and non-dominant solutions go to the external population. The source code can be downloaded from the website of Xinfu. He was in England for many years. He moved to Hong Kong. I think he now has a new website on MOIA-D. It's just, I don't remember where is it, but you can go to this one. This one still works. And you can find here all his source code. So this is the original MOIA-D. So you can see he has the code in C++ for continuous and knapsack problems. Then he has a MATLAB version, a Java version. And then he has the version that he used for the paper of 2009 that we just saw on these complicated Pareto sets. This is the version that won the competition in 2009. And for example, this one is for expensive objective functions. It uses Gaussian processes. That's surrogates. We will talk about surrogates towards the end. That one is also available. But there are many others. These are not the only versions of MOIA-D. He has quite a few others. It's a parallelization. And he has one. This is for circuits. And he has one with simulate annealing. He has one with simulate annealing. And a MOIA-D. This is for combinatorial problems. This is a MOIA-D for combinatorial problems, which we tried once and it was not very good. But I don't know, he probably has a better one now. So you can see he has quite a few papers and implementations. So this is the second algorithm that is very popular. It is actually the most popular right now. The third is SMS-IMOA. We talk about this one as well. This is a steady state version of energy A2 in which instead of hypervolume, it uses, instead of crowding, it uses hypervolume. So it uses this reduced procedure, performs non-dominant sorting, same as energy A2. But in the reduced procedure, they use a selection criterion when dominant solutions are compared, two solutions that are in which one doesn't dominate the other one, because in energy A2, if one dominates the other one, that wins, right? But if this solution does not dominate the other one, there is a tie, they are non-dominated between themselves, then they apply crowding. They measure the value of crowding, and whoever has the larger value wins. In this case, they use hypervolume. They see which of the two solutions contributes the most to the hypervolume. Okay, and that's, this one, I think the code is not available in the public domain, except in JMetal. In JMetal, you can find it. Okay. So any questions? Because we're about to start. I think I left this one open. And this topic is a bit difficult. I hope I don't get you dizzy with this one. It's a complicated one, performance indicators. I will try to explain as much as I can on this topic, but it's difficult to understand. I always tell my students, if you don't understand performance indicators, don't worry. All you have to do is to implement them, and that's it. You don't have to understand how they work. Understanding is sometimes complicated. Yeah, the good thing is many of these indicators are already implemented. You can get them in the public domain. Okay, so we went first from describing algorithms, then we described test problems. We saw a wide variety of test problems. Of course, if we have test problems and algorithms, we need some means of knowing that algorithm A is better than algorithm B. Otherwise, we won't be able to publish any paper, right? We need to be able to show to other people that our algorithm performs better than other algorithms. And that's the need for performance indicators. Performance indicators are relatively recent in this field. When I started in this area back in the year 94, we didn't have performance indicators. So we had to compare solutions in a very odd way, and I told you about that before, that people will write a paper in which they plotted the Pareto Front approximation produced by two different algorithms. And they say, for example, this is algorithm A, and this is algorithm B. And they will say, well, look how algorithm B is missing a portion here. So this was like a, an art appreciation class. You are teaching people how to look into pictures, but there were no measures. And then people say, well, isn't it possible that you produce something that can be used to assess performance in a numerical way? I don't want to see plots. I want to see numbers. And we said, okay, let's try to produce something that produces numbers. Then it turns out that these numbers were not reliable. That was very bad, but it took us some time to realize that. So Sizzler, in 2000, this is the same paper where Sizzler presented the ZDT problems. In this paper, he talks about performance indicators. And he says, okay, when we assess performance of a multi-objective evolutionary algorithm, there are three things that matter. We want to be able to minimize the distance between our approximation and the global optimum, right, which will be the Pareto optimal set. So we want to be as close as possible. It can be Pareto optimal set, Pareto optimal front, whatever you prefer. But we want to converge, right, to the true solution. We want a good distribution of these solutions, where good for us normally means uniform or equidistant. But this is something you have to keep in mind. This is possible if the problem is continuous. If the problem is discrete, in many cases, the true Pareto optimal front does not have a uniform distribution of points. So uniformity is sort of an artificial thing. And the last one is the extent of the obtained Pareto front should be maximized. This is important that you keep in mind, because I think yesterday somebody made a comment on this. People normally get confused with this. They say, okay, what do we assess with the hypervolume? With the hypervolume, we can assess convergence and maximum spread. What does maximum spread mean? That we reach the extremes of the Pareto front in our approximation. That doesn't mean the points in the Pareto front are uniform, that the distribution is uniform. It has nothing to do with uniform distribution. Maximum spread only means I was able to reach as far as possible towards the extremes of the Pareto front. And this applies in any number of dimensions. Okay? It's very difficult, it's very different to say that my solutions have a uniform distribution. Uniform means they are equidistant in the Pareto front.
So how do you know what the maximum spread will be as indicated?
The hypervolume. Whatever returns the hypervolume has the maximum spread. Whatever gives you the highest hypervolume has the maximum spread, always. So if my hypervolume is larger than yours, I got a better spread than you. It's just look at the value. It's implicit in the value. Okay, so those are the three things we want to do. Now, something important to keep in mind, these three goals, of course, they came from a computer scientist. That means they are not always desirable or even relevant. That's from a computer science perspective. For example, as I say, if the true Pareto front is not uniformly distributed, we're not going to ask for a uniform distribution of points, right? Because the true Pareto front is not like that. Also, what if the true Pareto front contains a single solution? So the spread will make no sense. Perhaps one solution is very extreme, but there are problems in which you only obtain 2, 3, 4 solutions. So talking about maximum spread, uniform distribution doesn't really make much sense. And this could happen in real-world problems, because real-world problems have objective functions that in many cases are very expensive to evaluate. So we will use a very small population, very few evaluations. Therefore, we will find very few non-dominant solutions. So in that sense, applying all these measures doesn't really make any sense at all. But we're talking, of course, about benchmarks. So normally the first goal is the one that matters, to be able to converge. Of course, if we don't know where is the Pareto optimal front, talking about convergence is difficult. However, since we have performance indicators such as the hypervolume, I can know by looking at the value of the hypervolume if one approximation is better than another one. This at least I could identify. So this is good enough, even though I don't know where is the true Pareto optimal front. Something interesting that was identified in the early days of the field is that this no performance indicator can assess these three goals, because assessing the three goals is also a multi-objective problem. Cannot be done in a single one. Okay, before we describe the performance indicators that we normally adopt, there are quite a few of those. We will give some definitions, what we call preference relations. These preference relations are taken from this paper from Joshua Knowles, and this is basically something important for understanding the properties of this performance indicator. As I told you, please bear with me. This is a bit abstract, a bit theoretical, but I hope you don't get lost. This, by the way, was used for many years. It's a tutorial these guys gave at IMO 2005 that we had in Mexico, in Guanajuato. And it's very, very nice paper. It's still available, although today is not that important as it was 10 years ago. They give an introduction to performance indicators and how to use them, how to apply performance indicators, particularly binary performance indicators. Okay, so these are the relations. We have strictly dominates is represented with the double preg. So this means that set 1 is better than set 2 in all objectives. This is a strict dominance. You know, I'm really above you, clearly. Dominates is the one we already know, a single preg. So set 1 is not worse than set 2 in all objectives and is better in at least one. It's the same Pareto optimality, just saying this in a different way. Weakly dominates, you see, has the equal here. This means set 1 is not worse than set 2 in all objectives. Incomparable, I put the double bar, neither set 1 weakly dominates set 2, nor set 2 weakly dominates set 1. And indifferent is different from incomparable. Set 1 has the same value as set 2 in each objective. So that means they are identical. There is a difference between incomparable and indifferent. So they are defined on the basis of objective vectors, right? All of this is objectives, not decision variables. Also, we can use reverse arguments, and all this will hold. Okay. Now. Mm-hmm.
Sir, in some of the papers I have seen the sign for weakly dominates is actually for the dominates.
No, it's not the same.
In some of the paper I have
Yeah, well, they are wrong because it's not the same, sure. They are not the same. Weak dominance produces more solutions than dominance. If you remember when we saw the definition, weak dominance means that you are using only that is less equal in every objective. We remove the strictly better in at least one. So it cannot be the same. That produces more solutions than Pareto optimality. But some algorithms use weak dominance. It's true. There are some algorithms that use that. But it's not the same as Pareto optimality. Okay. Now, interpretation in objective space, again, strictly dominates. Every set 2 that belongs to B, and I assuming I have in objective space A and B. This means that every set 2 in B is strictly dominated by at least one set 1 in A. Dominates every set 2 in B is dominated by at least one set 1 in A. We use now better with the triangle. A is better than B if every set 2 in B is weakly dominated by at least one set 1 in A, and A is different from B. Weakly dominates, every set 2 in B is weakly dominated by at least one set 1 in A. Incomparable, again we use the double bar. Neither A weakly dominates B or B weakly dominates A. This is exactly the same definition we saw before. And indifferent, we use this tilde, is A weakly dominates B and B weakly dominates A. So it's different. You see the difference in objective function space. And again, we can use the inverted relations. And in this case, if we use A strictly dominates B, implies that A dominates B and A is better than B. Okay? So, now using these relations, we are going to analyze some of the main performance indicators that we have available. Joshua, in his paper, he follows the work of Hansen and Jaskiewicz from '98, who consider the problem of evaluating approximations to the 3 Pareto Front. And for doing that, they define some outperformance relations. These outperformance relations express the relationship between two sets of internally non-dominated objective vectors. We're going to be using A and B for the two, as in the previous slide. So, for example, NDS, in this case, it denotes the non-dominated points in S. So, weak outperformance implies that the non-dominated set of the union of A and B is equals to A, and A is different from B. So, in this case, A weakly outperforms B if all points in B are covered by A. Cover means is equal or dominates. And there is at least one point in A that is not contained in B. Weak outperformance is good. It means A is better than B. A is the approximation of one algorithm, and B is the approximation of the other algorithm. Remember, we are operating with sets of solutions. So all this analysis I will show you is related to that. If the indicator can or cannot tell me if one is better than the other. In many cases, you will see the algorithm, the performance indicator is unable to tell me if approximation A is better than approximation B. And this is the puzzle about performance indicators. So we have a strong outperformance, complete outperformance, and the weakest version is this weak outperformance. So for example, a strong outperformance is if all points in B are covered by points in A, and some point in B is dominated by a point in A. And complete outperformance is if each point in B is dominated by a point in A. So all of them are relationships between approximations to the true Pareto Front because they are compatible and only depend upon a standard Pareto dominance. So these are not metrics of performance. These are just relations that I'm going to use to analyze performance indicators. Hansen also defined compatibility and weak compatibility. So weak compatibility says a comparison metric is weakly compatible with an outperformance relation if for each pair of non-dominated sets A and B, R will evaluate A as being no worse than B. And compatibility is a comparison metric R is compatible with an outperformance relation if for each pair of non-dominated sets A and B such that A is less equal than B, R will evaluate A as being better than B. So these are, I think, more obvious to understand. Okay, so for each of the performance measures we're going to analyze, we were going to see three things. Pareto compatibility, and this is important for theoretical reasons, and then something more pragmatic, the advantages and disadvantages. The purpose here is to see how the performance indicator compares to approximations. There are several possible ways of doing this analysis. For example, a direct comparative measure will compare A and B directly using a scalar measure, which is normally what a performance indicator is. A performance indicator is a scalar measure. So if R of AB is equals to C minus R of AB for some constant C, then we say that R, which is this relation we're using, is symmetric. Another option is what we call a reference measure. A reference measure, and this is an important distinction. Joshua identifies between direct comparisons. There are performance indicators that directly compare the outcome of one algorithm with the outcome of another algorithm. This is what is illustrated here. But there are also performance indicators that are called reference measures because they use a reference set to perform the comparison. That means they don't compare directly the outcome of two algorithms. They take the outcome of algorithm A and compare with the reference set. Then they take the output of algorithm B, compare with the reference set. And whoever gives a better value is the better of these two algorithms. But you see the comparison in this case is not direct. Okay. Direct comparative measures can also be used as reference measures if we specify a particular reference set. However, the converse is not true because performance indicators that require a reference set, the reference set is normally the true Pareto Front, and this cannot be modified. This we cannot adapt. And finally, we have independent measures. Independent measures do not depend on any reference set or on the outcome of another algorithm. That's what they are called, independent. Finally, another important feature of a performance measure is if it induces a complete ordering of all possible non-dominated sets. If this is true, this ensures transitivity. So that if I compare A, B, and C, if A beats B and B beats C, then it is always true that A beats C. But this only happens if the performance indicator can ensure transitivity. Some of them can do it, not all of them. It is often the case that direct comparative measures do not induce a complete order. And the relations between different sets may be intransitive. So this is bad. This is bad. Intransitivity is always a bad thing. What we can do in these cases is to use reference sets, and that's what people does. So transitivity is not generally a problem with independent measures because independent measures tend to induce complete order. This is more a problem with direct comparative measures. And finally, that if a measure is a cardinal measure, which is based on counting the number of vectors in some set, we will indicate that, or we will say this is a non-cardinal measure. Some indicators rely on counting the number of vectors in a set. Okay. So Pareto compatibility is concerned with compatibility with the outperformance relations that we already defined, OW, OS, and OC. So the less compatible the measure is, the more misleading it may be. And the problem is, if it's misleading, the result that the measure produces is not reliable. That's really the problem. That we will put in the paper, look how with this indicator my algorithm outperforms NSGA2, NSGA3, whatever. But it turns out this is not true. This is what the indicator says. But the indicator, if it's not reliable, then it's not to be trusted. You cannot trust this result. So the hardest relation to be weakly compatible is OW, and the easiest is OC. So compatibility with OW is necessary and sufficient to ensure monotony, and sufficient but not necessary for ensuring relativity. So monotony is given a non-dominated set A, adding a non-dominated point improves its evaluation. It never degrades the evaluation. And weak relativity means the evaluation of the true Pareto Front is non-uniquely optimal. That means all other non-dominated sets have a strictly inferior or non-superior evaluation. So having weak compatibility with OW is good enough. If an indicator has that, that's it. We are safe. And for analyzing advantages and disadvantages, we will consider several issues, including compatibility with the outperformance relations, computational cost, if they are scaling independent. That means, is the ordering of approximations affected if one objective is scaled relative to the others? And also, if the indicator relies on knowledge of the true Pareto Front or any other reference set or point, and whether it can differentiate between different levels of complete outperformance. So this means that if we have three approximation sets, A, B, and C again, with A, OCB, and B, OCC, the question is if the measure will give a different evaluation if A and B were compared than if A and C were compared. So in this case, of course, we are questioning the transitivity of the performance indicator. Okay, so we will start with the hypervolume because this is the nicest of all performance indicators. Proposed by Sizzler in '99, is defined as the area of coverage of PF known. This is our approximation of the Pareto Front with respect to the objective space. And this is equal to the summation of all the rectangular areas bounded by some reference point, which will be F1, F2 for B objective case. So it's described mathematically like this. This is an independent indicator. in the sense that it's not necessary to have the outcome of the other algorithm, and it's not necessary to have a reference set. However, we need a reference point. It induces a complete ordering and is non-cardinal. It doesn't count things. It just gives me a real number, a numerical value. Is compatible with OW, provided that the reference point is set so that all feasible non-dominant sets are evaluated as positive. And this is an important point that should not give me negative numbers. Normally, we use the worst objective function values to define this reference point. So advantages is compatible with the outperformance relations, is independent, differentiates between different degrees of complete outperformance of two sets, is scaling independent, and its meaning is kind of intuitive. Disadvantages, well, it requires defining some upper boundary of the regions within which all feasible points will lie, and this does not affect the ordering of non-dominated sets and is relatively arbitrary. The main disadvantage, as I told you before, is that it has a very large computational overhead, which makes it impossible to use it for many objective optimization, although in the last few years there has been a lot of research in this regard. Another subtle caveat of hypervolume is that it multiplies different objectives together. Although this is not supposed to matter because the indicator is scaling independent, in any case, this is something you have to keep in mind. Because you saw the definition, it will take the union, so this means these areas are going to be multiplied. But this is about the best indicator we have. So even if you didn't follow the whole explanation, the summary is this is an awesome performance indicator. It's as good as we can have of an indicator. But it's too costly. That's the disadvantage. Theoretically, it's the best. There is nothing better than hyperbola. It fulfills everything. It is reliable as long as I define correctly the reference point. How do you know if it's incorrect? If you get negative numbers. You get negative, you screw up with the hyperbola. Because when this restriction that it says that all feasible non-dominant sets are evaluated as positive is because basically with the hypervolume, what you are doing is to compute a volume with respect to a point, right? You are computing this. If you took numerical methods, in numerical methods, when you do the integral under the curve, one of the things you have to consider is, for example, if you have something like a sine, you will compute one area, another area, but this area is negative. So if you add the negative to the positive, they cancel each other, and you will have a zero area, which doesn't make any sense. The same will happen with the hypervolume. If you choose wrong the reference point, you will have a portion of the volume that is negative. And if you add it to the other volume, it will cancel with that one. And the value you get is not reliable. So all you have to make sure is that this never happens. And normally the way to ensure that is to use worst objective function values. If you do that, that's it. Normally it will never be negative. You are never underestimating the reference point.